Frames and machines are not that complicated to deal with, but they can be time-consuming. When trying to find the reactions inside of either of these, it becomes necessary most of the time to break them down into as many pieces as possible, each with their own free body diagram. After you have each free body diagram, you can draw in the force reactions, usually consisting of pins and two force members. Often it is required to pass forces that were derived from one free body diagram to another. The points that we're connecting to one another must have their forces reversed when looking at different free body diagrams. I'll demonstrate this further in the next slides. Here's an example of a frame. This frame is simple enough to find the reactions at point A, B, and D. These can all be treated as pin reactions. If I draw a free body diagram of the entire object, you couldn't find the reactions at point A and D. But when you break it up into separate parts, you usually can find the reactions. When I break it up, I need to draw the forces that are reacting at pin B. But since it is the connecting force reaction between the free body diagrams, we have to make sure the signs are opposite. That means that if I assume that my BX and BY are positive in one free body diagram, they need to be negative in the other. Now to solve this problem, I usually write all of my equations for all free body diagrams. I maintain my assumptions throughout the entire time. My first set of equations relate to the right free body diagram, summing forces in the x and y directions, and then taking a moment about point D. As you may notice, there are 4 unknowns in the free body diagram. Therefore, this free body diagram is insufficient to find all the unknowns. Therefore, in order to find all the reactions, we need to look at the other free body diagram. The second set of equations corresponds to the second bar. Notice how I maintained the assumptions of the directions of B, but they are now going in the opposite direction as they were from the initial free body diagram. Notice how I still have 4 unknowns in the second free body diagram, yet only 3 equations. So I can't solve for all these reactions by themselves, but I can solve for them if I use the equations together. Since both sets of equations hold the bx and by terms constant, I can pass forces from one free body diagram to another. I would first look for the equation with the least number of unknowns. This should be obvious as the moment at point D from the first set of equations, because it only has by as an unknown. That means that I can solve for by and then dy in the first set of equations. After finding by and dy, I notice that I can't find anything else in this first free body diagram. So I'll transfer what I do know over to the second set of equations. When I put my value in for by, I notice that my moment at point A and my sums of the forces in the y direction becomes possible to solve. First, I'll find the moment at point A, which will give me bx, and then I'll sum forces in the x and y directions to find ax and ay. Finally, I'll bring back what I've found from the second free body diagram over to the first, and now I can find my force for dx. And with that, I have all the reaction forces and this problem is solved. Now, after learning about frames, machines should be a piece of cake. Looking at this table clamp might seem difficult at first, but luckily it isn't so hard. First, what we need to do is identify the force reactions that occur within the machine in order to find the compressive force at point E. Since we are looking at the compressive force, we can treat it as a normal force acting at point E of the clamp. Next, we should notice that the bar attaches to point E has 2 pins. Finally, we should notice the little bar CD is going to act as a 2-force member. I wouldn't try to solve for the reactions on the fixed table support. They are a bit too complicated to deal with right now. Now that we have identified our forces, we should have an idea of what we want to find. I'll separate the 2 bars like this, and I'll put the respective forces where they go. Notice again how I have different directions of the forces where the 2 come together. Now that we have gotten to this step, the process is the exact same as it was for the frames. All we need to do is set up our equations and we can solve for our unknowns. In total there are 6 unknowns, but we only truly care about finding the compressive force at point E. So setting up my equations for the first bar gives me the following. Now that moment equation might seem daunting, but that is where we have to start. I'm taking the moment at point A, and because of that I can find the force in the member CD. There's so much in that equation simply because there is an x and y component to both of the force and the 2-force member. Next, I'll set up my equations for the second free body diagram. If you notice, taking a moment at point B tells us that if we know what AX is, we can find the compressive force at E. I would suggest trying to find AX as quickly as possible, probably by using the moment at A from the previous free body diagram, and then summing forces in the X direction. I am going to be thorough, however, and solve for all the reactions, which can be found after taking moments and summing forces in the X and Y direction. And here we have our final force at E, our compressive force of 51.7 pounds.